Swayam Prabha. Digital India. Educated India.
Hello and welcome to the second week of instruction of this NPTEL online course on advanced process dynamics. In the previous week we focused on linear systems, and in linear systems we focused on linear autonomous systems. We took the examples of first order systems and typically saw how the behavior of first order systems would be. So, if you model a first order linear autonomous system as dx by dt is equal to f of x, where f of x is equal to a x to make the system autonomous, then your solution will be of the form x 0, where x 0 is the initial condition, multiplied by e to the power a t. So, dx by dt is equal to a x, or a similar variant of it will have the dynamics which will follow x 0 multiplied by e to the power a t, or a similar variant. We saw that this dynamics will always be monotonous, which means that depending upon the value of a, the dynamical variable x of t would either continuously increase with time, thereby diverging to infinity, or it would always decrease with time, thereby converging to a constant value as time t tends to infinity. In this week we will take second and higher order systems. We will realize that higher order dynamics are inherently difficult as well as inherently different in certain features when compared to first order dynamics. So, let us see and how we can model second and higher order dynamics, and where do we come across such situations. On the left hand side you see the example of water level in a tank, which we considered in the previous week, where there was one equation, one dynamical equation given by dH by dt is equal to 1 over a q 1 minus q 2, where q 1 is the input flow rate, q 2 is the output flow rate, a is the area of cross section of the tank. The order of the system is 1 because we have one dynamical equation, and the equation is first order ODE, and the dynamical variable in this case was h of t. Now, you imagine that the output from the first tank, this one, is fed to the second tank. So, in the figure on the right hand side you have the output from the first tank, and this output is fed as an input to the second tank, and you have the ultimate output from the entire system as q 3. So, now we can write similar balance equations as dH 1 by dt, where h 1 is the level of liquid in first tank, is equal to 1 over a 1, where a 1 is the associated cross section area of the first tank, multiplied by q 1 minus q 2, and dH 2 by dt, where h 2 is the level of liquid in tank 2, is equal to 1 over a 2, where a 2 is the associated cross section area of the second tank, multiplied by q 2 minus q 3. Now, you see that we have equation 2 here, which is a first order ODE, and equation 3 which is the second which is also a first order ODE, and altogether equations 2 plus equation 3 describe the dynamics of the system. Therefore, the order of the system is 2 in this case. So, we have actually obtained a second order system by considering two simple first order equations. But in this case the dynamical variable is represented as h 1 t, h 2 t, and capital T in the superscript here represents the transpose. So, let me write here transpose. Okay. So, you have a vector. So, we will define a vector as a column matrix. So, dynamical variable would be a vector. Okay. And what would be a vector in our case? It would be a column matrix. So, matrix of the form x 1, x 2 and for an nth order system up to x n. Okay. So, this in fact is a matrix, but this is a column matrix, and therefore, we would refer this column matrix as a vector, and the dynamical variable in such a case would be simply a vector. So, for the case given here, you have a dynamical variable which is a vector given as h 1 t, h 2 t, or alternatively h 1 t, h 2 t transpose. Okay. So, there are two ways of writing this. You can write this as h 1 t, h 2 t, which is equivalent to writing h 1 t, h 2 t transpose. So, this will be our notation for representing dynamical variables in higher dimensions. So, now we can write a general nth order equation or nth order system, dynamical system, by simultaneous equations which are given here. Now, what is the genesis of these equations? Let us consider the previous case where you have the input q 1, input q 1, output q 2 goes as the input to the second tank, and you get the output q 3. So, this is h 1 and this is h 2. Now, our dynamical equations were d h 1 by d t is equal to 1 over a 1 q 1 minus q 2. So, let us consider a case where q 1 is 0 and q 2 is simply a linear function of h 1. So, you have a valve which would vary the flow rate, which goes as A times h 1, and we have d h 2 by d t is equal to 1 over A 2 q 2 minus q 3, and q 3 would go as B times h 2, right. And for the ease of representation, let us consider unit cross sections of both the tanks. So, I can write here d h 1 by d t is equal to minus of A h 1, okay, and d h 2 by d t is equal to A h 1 minus B h 2. Okay. So, we have these two equations, and what we see is that we have the equations which are coupled. So, this equation for example, has h 1 and h 2 both. So, equations are coupled. In fact, you can always write this equation as plus 0 times h 2, and you will see that now you have converted the set of equations into individual equations where you have coefficients, and you have the components of your dynamical variables. Okay. So, therefore, you can write a general nth order system as a set of n first order ODEs which would be coupled, and therefore, the order of the system would be n. The dynamical variable would be this vector x 1, x 2 up to x n transpose, and you will give the individual equations as d x 1 by d t, which will be some linear combinations of the individual weightages of the individual components, similarly for d x 2 by d t and so on. Now, if this be the case, I can convert this set of equations to a matrix equation. Okay. So, this is how the matrix equation looks like. So, how would you get this matrix equation? Well, it is not very difficult. So, our original set of equations was this. So, how do I write this? I can write this as d by dt, and I will consider all these components of the dynamical vector. So, I can write this as x 1, x 2 up to x n, and this would be equal to a matrix multiplied by the dynamical variable, original dynamical variable. So, x 1, x 2, x n. So, this would be x 1, x 2 up to x n, and then the coefficients here a 1 1, a 1 2 and so on would go as the elements of the matrix. So, a 1 1, a 1 2 up to a 1 n, a 2 1, a 2 2 up to a 2 n and so on. So, this will be a n 1, a n 2 up to a n n, right. So, this is the matrix form of your dynamical equation. So, a dynamical system which is of general nth order can be expressed in terms of a matrix equation, where the dynamical vector will have n components and the corresponding matrix would be an n cross n matrix. Okay. So, let us see how does the equation look like. The equation looks like this: d by dt of the dynamical vector is equal to the matrix multiplied by the dynamical vector, and we will use this notation consistently throughout the course, where the vector would always be represented by an underbar, a single underbar, and a matrix would be represented by 2 underbars. Okay. So, therefore, this would be represented as x underbar, this would be represented by x underbar, and this matrix would be represented by a double underbar. So, therefore, I can write this equation as d x underbar by dt will be equal to a double underbar to signify that it is a matrix multiplied by x underbar again. And how do I compare and contrast this equation with a first order dynamical equation? An nth order dynamical equation is given by d x underbar by dt is equal to a multiplied by x underbar, and the first order dynamical equation is simply given as dx by dt multiplied by a x. So, the functional form of these two equations is in fact identical. All you need to do is, for a first order system, when you have x as the dynamical variable, you need to change it to x underbar to indicate that this is a vector, this is an nth order system, and the variable a which you have in a first order system has to be converted to a matrix a double underbar. And therefore, now you can do an analysis to find similarities between these two systems and also contrast the differences between these two systems. Okay. So, let us look into the details of how to handle such a system. So, we solved the equation dx by dt is equal to a x, the first order dynamical equation, simply as x 0 multiplied by e to the power a t. How do you solve an nth order system, or how do you solve a matrix equation? That is solved using this theorem. The theorem says that the solutions to a linear autonomous equation of the form dx by dt is equal to a x. In fact, this is the equation which we are currently dealing with. We want to find the solution, is given as summation I goes from 1 to n, where capital N is the number of components in your system, C I, where C I are the constant multipliers, constant multiplication factors or multipliers. In fact, one would realize that these are the members of the field over which the linear vector space of the solution is defined, multiplied by e to the power lambda I t. T very clearly is the time, but lambda i's are the eigenvalues, and v i's are the corresponding, it is very important, corresponding eigen vectors. Okay. This is important that you make absolutely sure that when you use eigenvalues for your matrix, which matrix, by the way, this is the matrix A. Okay. So, you have an n cross n matrix in your system, n cross n matrix in your system. So, you would determine the eigenvalues of that n by n matrix A, you would determine the corresponding eigenvectors, and then your solution would be given as x under bar is equal to n I going from 1 to n C I e to the power lambda I t multiplied by the corresponding eigenvectors. Can we see whether this is in fact the case always? Let us see. So, we have the equation which is given as dx under bar by dt is equal to a double under bar x single under bar. This is the equation that we have. Now, the solution that we have is given as x bar is equal to summation I going from 1 to n C I e to the power lambda I t multiplied by the corresponding eigenvector V I. Okay. Now, if x is the correct solution to this equation 1, then if I substitute x on the left hand side and I substitute x on the right hand side, then I should get identical expressions, right. So, we can test this. So, if equation 2 is the correct solution, then dx under bar by dt would be d by dt of summation I equal to 1 to capital N C I e to the power lambda I t V I under bar, right. So, I would do some rearrangements. This can be written as I going from 1 to capital N. Now, inside the bracket, the only quantity which is a function of time is e to the power lambda I t. C i's are constants and all the entries in V i's are also constants. So, therefore, I can write this as C I V I d by dt of e to the power lambda I t. Okay. And then I can do a differentiation where I can write this as I going from 1 to capital N C I V I under bar. This will become lambda I times e to the power lambda I t, okay, e to the power lambda I t. So, let me do some further rearrangements. This would be 1 to n. Now, I write this previous expression as C I e to the power lambda I t multiplied by lambda I v I. All I have done is that I have taken e to the power lambda I t here and I have taken v I bar under bar there. Okay. So, then what do we get? Now, I observe that in the bracket I have lambda I v I under bar, and what I know is that lambda i's are the eigenvalues and v I bars are the corresponding eigenvectors. And therefore, since A double under bar is my matrix, I can write A double under bar v I bar, where v I bar is as an eigenvector, is equal to the corresponding eigenvalue multiplied by v I bar, right. So, what I will do is I will substitute equation 4 in equation 3. So, what I get is d by dt of x under bar is equal to summation I is equal to 1 to capital N C I e to the power lambda I t, the operator A multiplied by v I bar, which further can be rearranged as I going from 1 to capital N C I. In fact, I can take A out and now I can write A C I e to the power lambda I t and v I under bar. But what is this in the bracket? This quantity is nothing but x under bar, see here from equation 2. Okay. So, I will take this out, I will take this in, which will give me A operating on I is equal to 1 to capital N C I e to the power lambda I t v I under bar, from where I can write dx under bar by dt is equal to A double under bar x single under bar. Okay. So, from equation 5 what we get is that in fact, if x is summation I going from 1 to n C I e to the power lambda I t v I bar under bar, then it solves the equation dx by dt is equal to A x, where x is the x under bar is the dynamical vector and A should be the matrix A double under bar. So, now how can this entire concept be probably used for solving a problem? Well, we can actually solve a dynamical equation. For example, I have a system of equation in front of me. So, the equation is d x 1 by dt is equal to minus 2 x 1 minus 4 x 2 plus 2 x 3 d x 2 by dt is equal to minus 2 x 1 plus x 2 plus 2 x 3 and d x 3 by dt is equal to 4 x 1 plus 2 x 2 plus 5 x 3. So, this is the dynamical system that I have. I have a third order system. I have 3 first order equations. These equations are linear. These equations are in fact autonomous. It is not very difficult to realize that these equations are autonomous, and these equations are coupled. You cannot solve for x 1, x 2 and x 3 individually. So, I will need to resort to the method which I developed just now. So, my equation can be transformed to a matrix equation, which would be of the form d by dt of x 1, x 2, x 3, the dynamical vector, and this would be equal to minus 2, minus 4, 2, minus 2, 1, 2, 4, 2, 5 multiplied by x 1, x 2, x 3. Fine. So, now what do I need to do for solving this equation? I need to determine the eigenvalues and eigenvectors of A. So, in fact, I have those eigenvalues and eigenvectors already determined with me. So, the eigenvalues are lambda 1 is equal to 3, lambda 2 is equal to minus 5, and lambda 3 is equal to 6, and the corresponding eigenvectors are V 1 is equal to 2 minus 3 minus 1 transpose, V 2 is equal to 2 minus 1 1 transpose, and V 3 is equal to 1 6 16 transpose. I assume that you still know or remember that the method to calculate the eigenvalues and eigenvectors of a square matrix. Please go back and try to recapitulate the method in case you have forgotten. So, this is the set of eigenvalues and eigenvectors, and therefore, I can write x 1, x 2, x 3 as C 1 multiplied by e to the power 3 t, 3 coming from here, multiplied by 2 minus 3 minus 1 plus C 2 e to the power minus 5 t multiplied by 2 minus 1 1 plus C 3 e to the power 60 multiplied by 1 6 16, right. This is my solution. Now, what I do not know yet is the multiplicative constants C 1, C 2 and C 3, but those are not very difficult to determine. For that, I will need the initial conditions. Okay. So, let us say that the initial conditions are given to me as x 1, x 2, x 3 at t is equal to 0, say 0 0 0, just for an example. Okay. So, what will happen? I will substitute this here, and I will substitute t is equal to 0 in all of these cases. So, it is not very difficult to see that what you will get is an equation of the form two 2 1 minus 3 minus 1 6 minus 1 1 16 multiplied by C 1 C 2 C 3 is equal to 0 0 0, right. Now, this is a simple matrix equation which corresponds to a set of linear equations which are coupled, and you need to solve it for C 1, C 2, C 3. You can do it by changing it into an upper triangular matrix using Gaussian elimination and then you can determine the values of C1, C2 and C3. So, I leave this as an exercise for you to determine the values of C1, C2 and C3 from this matrix equation, and then substitute that in this equation number 6 to get the solution for dx1 by dt is equal to minus 2 x 1 minus 4 x 2 plus 2 x 3 and so on, which is given here. So, now we have a method by following which we could easily determine the solutions of an nth order dynamical system, which can be cast as dx bar by dt is equal to a double under bar x single under bar, which looks like an eigenvalue problem, which in fact is an eigenvalue problem. This is a linear autonomous nth order system, and the solution for this system is given as summation I going from 1 to capital N C I e to the power lambda I t multiplied by corresponding eigenvectors. So, while you can use this method for systems of any order, something which is of particular relevance as well as particular interest for process industries is second order systems. Second order systems are not only found amply in process industries as well as in general physics and also in nature, but they also pose a very good example for the study of further higher order further complex systems. So, what we will do is that we will take the example of second order systems, and we will try to understand the dynamics of second order systems in the rest of the lectures in this week. Thank you.